During a readiness test in the American West, a Minuteman III rises from a hidden silo and begins a journey few ever witness. This missile can travel more than 6,000 miles, crossing oceans and continents in a single arc. Today, we follow every step of that flight, from ignition to impact, and uncover what these tests reveal about U.S. nuclear preparedness. Before we open the blast door to this story, hit like, subscribe, and stay with us as we step inside America's most powerful deterrent. Moments after launch, the missile cuts through layers of atmosphere with controlled acceleration. Its sensors read temperature, pressure, and vibration as the first stage motor burns. Each reading tells engineers whether the vehicle is behaving as expected. These early seconds matter because any instability here affects the entire trajectory. As the missile climbs, the command center tracks every channel of telemetry. Operators verify thrust levels, casing temperature, and engine timing. The goal is simple: confirm that all systems match the expected launch profile. These measurements show how well the missile performs when conditions are real, not simulated. When the first stage separates, the vehicle loses weight and gains efficiency. Sensors detect the separation shock and verify alignment before the next motor ignites. Engineers compare these readings with previous launches to evaluate long-term reliability. Every test adds to a record built over decades. The second stage motor provides the thrust needed to shape the missile's long arc toward the Pacific. Telemetry confirms stable burn and minimal deviation. Analysts watch closely because even small changes in thrust can shift the final impact by miles. This is where precision begins to show. With the second stage complete, the vehicle transitions again. The guidance system checks its position against internal sensors, adjusting attitude through microthrusters. These corrections are minor but critical. They ensure the missile stays aligned with the planned path laid out before launch. As the vehicle advances, engineers examine its structural data. They look for unexpected vibration, temperature spikes, or signs of mechanical stress. Tests like these confirm whether older hardware maintains stability under extreme conditions. Consistency across flights is one of the most important indicators of readiness. Telemetry shows the missile holding a stable posture. The guidance unit compensates for small atmospheric variations, keeping the vehicle on track. Operators compare these adjustments with projections created before launch. A match here means the system's predictive models remain accurate. The missile approaches the point where final corrections matter most. Sensors monitor rotation, tilt, and stability. Engineers confirm whether these values remain within acceptable bounds. This phase determines how cleanly the test warhead will separate later in the mission. With the vehicle stabilized, the system checks orientation one last time. Guidance software tracks velocity, altitude, and descent angle. Analysts review these numbers to confirm the test payload can continue independently. Any mismatch is flagged now, before the separation sequence begins. The missile nears its separation window, and the system verifies speed and descent path. Analysts use these readings to judge how the weapon would behave in real-world conditions. These tests help measure long-term reliability. If you're following this to understand how modern nuclear testing works, consider subscribing for more breakdowns like this one. With conditions steady, the system runs its final checks before releasing the test payload. Sensors confirm structural stability and aerodynamic alignment. These values show whether the missile can handle the forces of re-entry. When all instruments agree, separation is authorized. As the descent phase begins, tracking transfers to land and sea stations across the Pacific. These units receive the last telemetry bursts before separation. Analysts study the incoming data to ensure the test payload is following its planned descent corridor. Accurate tracking here is essential to measuring final precision. When separation occurs, sensors detect the shift in mass and signal that the payload is free. The test vehicle begins its independent path toward the target zone. Engineers check for unwanted spin or instability. The quality of separation strongly influences re-entry accuracy. As the payload descends, speed climbs and atmospheric heating increases sharply. Radar operators track the compressing air around the vehicle. These readings help determine whether the structure withstands re-entry conditions. Each measurement contributes to understanding how the missile performs under extreme stress. During hypersonic re-entry, the payload generates strong shock waves and heightened temperatures. Field teams across the islands record sound, light, and pressure. These observations verify the final leg of the trajectory. Re-entry is where precision is confirmed or lost. A few miles above the ocean, conditions intensify. Friction raises temperatures, and the shock wave grows louder. Air, sea, and airborne platforms synchronize their instruments to capture every detail. These combined readings help reveal the payload's exact path in its most turbulent phase. In the final seconds, the payload drops rapidly through dense air. Acoustic sensors pick up the growing pressure wave. Ships move into alignment to record the impact. These last measurements confirm whether the missile remained accurate all the way to the target. The test payload strikes the designated point in the Pacific. A burst of light, a shock wave, and a thermal pulse confirm impact. Each platform, optical, thermal, acoustic, and maritime, records its own version of the event. Together, they verify the missile's end-of-flight accuracy. After impact, platforms transmit their data back to the analysis center. The goal is to confirm that the missile landed within the predicted zone. These records include heat signatures, shockwave intensity, and pressure changes. Combining them gives a complete picture of how the test performed. With all readings assembled, analysts compare the measured accuracy with the expected values. This determines whether the missile met the standards required for readiness. The results form the basis of the official test report, a key step in maintaining confidence in the Minuteman III system. Once field operations end, teams recover their equipment and verify that all data reached the command center. Proper handling ensures nothing is lost to weather or interference. These final checks make sure the dataset used for evaluation is complete and reliable. Analysts review the missile's behavior across each stage of flight. They compare performance with historical tests to measure long-term consistency. These evaluations support America's strategic posture, ensuring that the nuclear force remains credible even decades after deployment. With preliminary reports finished, the team confirms that the readiness test achieved its objective. The data now moves to Strategic Command, where the missile's overall performance is evaluated. Each test strengthens the long-term reliability of the U.S. deterrent and informs decisions about future readiness.